The question was, why would I want to give this talk? What is it about? Why do we care about cryptography? How does it work? And then what makes it work? So what was near and dear to me is explaining what you do and being able to do that in a simple way so that other people can understand, what is your job. I like to take that into anything that I talk about. So I'm trying to talk about cryptography as if everybody in the audience is 5. So I am literally here to insult your intelligence right now. We're going to go over some very simple theories and things like that. There will be a couple you probably don't know, and that's okay. But the base education level in this room says you probably know half of what I'm talking about. The question is, can you explain it to somebody that doesn't understand any of this, right? And I started thinking about cryptography, and everybody knows, okay, there's keys and cryptography and all this stuff, but like, how does it work, right? Oh, it does something. Well, what does that mean? So that's why I'm doing this, because I thought it would be interesting. So basically, the concepts that follow are incredibly, it doesn't really matter, right? Like, I could put a ton of text up there and tell you how you should think about it, but really, the important thing is everybody should know how to say this in a simplistic way, right? And I think that cryptography in general is very important, and a lot of these things that we kind of glaze over as a people in technology, we should go into more depth with individuals, especially people that don't understand it, to better understand little pieces of what we do that are kind of critical to them. So, what is it? I defined it like this. It's an arm race to obscure data long enough for the contents to no longer be useful by the time it is able to be read by an adversary, right? Mathematicians are working around the world to break codes. New discoveries lead to more secure systems in way of breaking older algorithms, right? So they're constantly fighting each other. If somebody asks you, just say, it's a nifty way of hiding things, right? And crazy math people made it up. Like, that's really the answer there. Cryptography is kind of the cornerstone of the modern internet, right? We need a way to securely communicate with people. And my way of saying that, it's the way of protecting those pictures of your stuff that you might not want other people to see until long after you're dead, right? So how does it work? Most of the people in this room would know that it works via keys, right? And the most simple version of that I could come up with is talking about Caesar ciphers. So who all knows Caesar ciphers, right? So Caesar cipher is a really simple key where you might transpose some text into some other text in order to obscure it in some way, right? So this has literally been used forever. None of this is new concepts. And the idea that you might take that text and jumble it up in a way, so there you can see it, jumbled up, right? So that somebody that's looking at it can't read it, right? Pretty simple. So the idea there, though, is that we need some key in order to better understand what this text means now, right? The problem with this kind of key, obviously, is that we have computers, and computers are capable of parsing all this apart very quickly and figuring out what the original text was. So this kind of key generally isn't going to work anymore. Here's an example of that, is by taking all of those different pieces of text and putting them into different pieces, which letters are being reused, everything else, you're able to go through and kind of determine what the original sentence was, right? Based on vowels and all this kind of stuff. So that doesn't work as well anymore. So this is an example of a key, but we're not going to do that. But more specifically, this is an example of a symmetric key, right? And I'm not going to go into all the math on how every single kind of key works, but symmetric keys do pose a problem in that eventually you have to give somebody that key in order to better understand your message, right? And as you start giving away that key, I think everybody in here would get the analogy that if you hand somebody a key to your house and they make a copy of it and that person makes a copy of it and that person makes a copy of it, eventually you don't have any security anymore at all, right? Anybody can read your message and do anything they want with it. Now, there is a distinct advantage of symmetric keys where everybody has the same key. Generally, it's much faster for a computer to calculate, to encrypt or decrypt a message with a symmetric key. But what if there were a better way, right? And this is when those crazy math people got together and went, I got an idea. What if we had two keys? One that could encrypt a message and one that could decrypt a message, right? And that's when we got to the concept of asymmetric key encryption. Still not working. There we go. Where we would use a public key that we would give out to the internet or whoever in order to be able to jumble up our message. but not be able to use that same key to get back the original direction, right? And so we need a second key, a private key, in order to do that work, where we would decrypt that message back to its original text. And for the longest time, this is all I understood about it, and I was done. And I was like, great, 2 keys. And the next piece of information that I had after that was just simply, okay, but somehow that works, and I don't really get it, right? And then somebody explained to me, okay, but it's just math, and it's really cool. There's a math problem that only works in one direction. And I went, uh-huh. And then I sat down with a pen and paper and started writing out math problems just as much as I could, and went, I can't write a math problem that only works in one direction, right? Like, we've been doing algebra for years. How do I do this? Like, I don't understand. I want to understand better. And that's what I did next, right? So this is the insulting your intelligence part. Asymmetric key encryption works by taking some original text, running it through a public key, basically, and coming up with a ciphertext that you can put out on the internet somewhere, right? Or in this case, because they're using the public key, it would be a message that's being sent to you. This is encryption. Somebody sends you that ciphertext. If anybody else were to intercept it, they couldn't read it. You'll use your public key to decrypt it, and now you can read it, right? So you're the only person that can read that message because it was sent to you using your public key. What I think is really interesting is you can switch the encryption and the decryption portions of that and go the other direction, where you can use your private key to do the same work, but you end up with something called signing, right? And generally, that's like an oversimplification, because you wouldn't sign your entire file. You would sign a smaller chunk. It doesn't matter. But the point is, it does work in reverse. And what this says to the world is, I'm the only person that could have written this content, right? And if you put the two together, which is really cool, once the clicker works, there it goes, you can end up with a secure communication, because you're the only person that could have wrote that message, and the other person's the only one that could read that message, right, by putting both keys together. So I think that that's really interesting. But again, I was like, okay, but how does it work? I can't write this math problem. Show me how it works, right? And what I came up with is it's magic. That's the only answer. And really, Renato, I don't know how you wanted me to cover any more time than that. So in reality, it's what I've been saying the whole time, right? It's math that makes it work. So I'm actually going to take you through the math on how cryptography asymmetric key encryption works. I thought it was brilliantly interesting and really simple. I never expected it to be this easy. You can literally do it on a napkin if you want to right now and follow along. I hope you brought your calculator. So what do we need to do in order to understand this? The first 3 that are up there, prime numbers, exponents, and modulo division. Everybody knows? Most people know. How many people know? Good. We're going to breeze through those. Those are pretty quick. But that's all grade school math that you've probably already learned. You might not know the name of them, but you've probably already learned it. The 2 at the bottom are a little bit more difficult. The concepts are simple, but we're still going to go through them, and you'll better understand how this works, right, from a mathematical perspective. So the first thing, prime numbers. 253. The definition of a prime number is a number that cannot be formed by multiplying 2 smaller numbers, right? It's a different way than you've probably heard it before, but there it is. Now, the clever among you might realize that's not a prime number. Okay? But the point that I'm trying to make here is that when you are using asymmetric key encryption, the way that it works, that the foundations is a math problem that's really easy in one direction and really hard in the other direction. So this is 2 prime numbers multiplied together. And as a human, it is really difficult for us to figure out that that's 11 and 23, right? Now imagine if those prime numbers were 600 digits long, which is what you generally have in something like an RSA encryption. That math problem basically becomes impossible, not only for humans, but for computers as well, right? So really easy math in one direction, really hard math in the other direction. You're going to see that as a theme. So the next one that we need to worry about is exponents. And in this case, it's a power to which a base number is raised by multiplying it by itself. So most people know that like 2 to the second power is 4, right? So who knows this one? Again, same concept, a math problem that's easy in one direction, but like almost impossible in the other direction, right? So this is 7 raised to the power of 11 when the clicker works. Maybe that's why everybody stands on that side, right? The clicker has a better signal. This is really hard for computers, if not nearly impossible, right? Especially, again, imagine both of those numbers are 600 digits long. Make sense? The last one is modulus division, or modulo division. Everybody in here probably learned this. By the way, don't waste your time trying to animate long division. Like that took way longer than it should have. Most of us know this, we just don't realize it. Modulus division is the remainder, right? Remember that in grade school where you're like, oh, I don't want all those decimal points. It's just the remainder, right? So in the case of this, we get 1. But what's interesting is that if we were to divide that really long number we had before by 3 and get the remainder, it is also 1, right? So this is basically impossible for a computer to ever reverse back to the way it was. If I gave you the number 1 and said, give me 2 prime numbers that when one's raised to the other and then divided by 3 comes up with 1, you would never in a million years come up with 7 and 11, right? You could try it a bunch of times, but again, you're not really able to work backwards from that 1. So all 3 of those kind of laying out the concept that one direction it works, the other direction it doesn't. Now the other 2, multiplicative inverses. This one is way easier than it sounds, but most people have never heard of it before. It's literally 2 numbers multiplied together equal 1. So for the most part, you're just going to say 10 and 1/10, right? Or 100 and 1/100th. You multiply them together, they equal 1. It's really, really boring until we include some of the other pieces of math that we've done before, right? Because it's always just going to be kind of the inverse of it. And then Euler's totient. Anybody heard of Euler's totient? Cool, a couple people, that's great. So Euler's totient, this one was the one that made me go, because if you look at the definition there, a number of positive integers that are relatively prime to x. And I got to half of those words and just went, I have no idea what they're saying here. But basically the concept of relatively prime means that those 2 numbers do not share a common denominator, right? So in the case of 4, the answer to Euler's totient is 2. There are 2 numbers that do not share a common denominator with 4, and they are 1 and 3. Make sense? So if I go to the next one here, which is 8, you'll see that it has 4, right? 1, 3, 5, and 7. I think that that's pretty interesting. But I think what's way more interesting is that 12 also has 4. They're not the same 4, right? That's pretty cool. But the one that we really care about is that a prime number, like 11, has 10 of them, right? Because it is prime, it does not share any common denominators with any other number, so it's always going to be 1 less. And that's Euler's totient, is basically saying that the numbers that are relatively prime to a number, if it is prime, is 1 less than that. So we're going to keep that in mind as we go through the next bit. But now we're going to step through it, and literally if you want to follow along, get out a piece of paper and a pen, and you'll be able to do this. So while we're going through this, if you want to try and keep in your head what the different things we just said were, follow along on either the left or the right or both. So we're going to look at prime numbers first. We have to pick 2 of them. They are P and Q. In this case, we're going to use 11 and 13, right? They're both pretty small. With that, we need to calculate a modulo, right? And the modulo will be used as part of our keys later on. And we do that really simply by multiplying those 2 together. So 11 and 13 together is 143. Everybody with me so far? Really simple math. From there, we need to calculate the Euler's totient of those same 2 prime numbers. So 11 becomes 10, 13 becomes 12. We multiply those together, we get 120. This is where the magic in all of this happens, right? So the first half of everything that we talked about really is all you need in order to make encryption or decryption work. Multiplicative inverses in Euler's totient are where we can actually calculate the keys that make it work together so that asymmetric key encryption works, where one key goes one direction and the other key goes the other direction, right? So that's why we need Euler's totient. From there, we actually just pick a third number, E, and it can be any prime number between 3, basically, is the smallest one we can use. You can't use 1, and whatever the totient was, so in that case, 120. I'm going to pick 7. In most cases, because these numbers are huge, right, 11 and 13 are gigantic, almost exclusively the number 65,537 is chosen. And the reason is because it is the largest known prime number that can be represented by 2 true bits in binary, right? You can see that typed out there, and that just makes it slightly faster for computers. So in our case, we're going to use 7. When we put 7 and 143 together, literally that's our public key. That's the whole math behind coming up with a public key, right? Normally this would be huge, but that's really simple. And then we have to use the rest of this formula here to figure out what is our private key. Make sense? So we're going to take our multiplicative inverses and work with that and the Euler's totient to figure out what is that going to be. So the answer to that question is 7 times some number equals 1 when divided by 120, and the 1 is the remainder. Make sense? So again, the math is not too terribly hard. Most of the time you would just try, kind of trial and error these numbers, but 7 times 103 is 721. Divide that by 120, we get 1, right? So 7 and 103 now have a really interesting relationship in that one of them is our public key and the other one is our private key. And if we multiply and use exponents and modulus division on some text, one is going to encrypt it and the other one is going to decrypt it. And again, my thing was just kind of going, wow, that was like way simpler than I expected it to be, right? So if we take that and we plug it into our actual example, right? And I'm going to encrypt the number 9 live on stage in my brain. Then what we would need to do in the next one you can see here where, C and M, like where did those come from, right? So C meaning ciphertext. Our ciphertext is literally whatever our message is, 9 raised to the power of our public key divided by that second portion of our public key, and you take the remainder, right? So 9 raised to 7 is, I'm going to pretend like I had this memorized, 4,782,969. We're going to divide that by 143, and we get 48. 48 is literally the encrypted version of 9 using that private or public key. Now, if we wanted to do it in the other direction, everybody get your mental math ready. This one's a little bit more difficult. 48 raised to the 103rd power is that number. It has 173 zeros, so good luck. But then we divide that again by that same 143, the second part of that private key, and we get 9. That loop closes, right? And it's basically impossible, again, to do it in the other direction, because if you can tell me that you can take 48 and multiply that by some random number of times of 143, and then you're going to figure out what these prime, it's never going to happen, right? So ridiculously kind of simple math that works in one direction but not the other. I'm also briefly going to talk about Carmichael's totient as opposed to Euler's totient. So Carmichael's totient is the one that's used more often now. Euler's totient is the really easy one, but this one is not terribly much harder. It's just you're taking the least common multiples of our P and Q minus 1 from before. Really, somebody figured out a while after Euler's totient went through that Euler's totient comes up with a much larger number than it needs to. Carmichael's totient takes a little bit longer to calculate, but the numbers are much smaller, which means computers can calculate them faster. And if the computer can do it faster, then we don't need to worry so much about the speed that this takes for asymmetric key encryption, because again, it's not as fast as symmetric, right? Basically, spend the time generating the keys, less time encrypting the data. Make sense? And then to recap, we're just basically saying cryptography protects things for at least their useful lifespan. We don't care so much that eventually all cryptography is going to be broken, right? Somebody else is going to give a talk, or probably will give a talk on, why this breaks in a quantum world. The simple version is the quantum computer tries every number at the same time. Oh no, like it's over. But we only care about their useful time span, right? If you're going to find anything on me that I wouldn't want you to know, I only care that it happens after I'm dead. The next bit is it works by using keys. So if you only learn one thing today, it works by using keys. I'm guessing you all knew that. Asymmetric keys come in pairs. It's pretty simple, right? We're getting there. So just additional things to kind of keep in mind if you're trying to explain this to somebody in the future. They work because the math works in one direction, but not the other direction, right? And then if you really want to go into it, the modulus and multiplicative inverses are what cause that to work at a deeper level. So these theories are really, really easy and hundreds of years old. Euler's totient, that guy wrote the paper on it in like 1760 or something like that. And it's just now that we have the computing power in order to do something cool with it. And this is literally how RSA works. Like that is the RSA algorithm. So if anybody was curious how that works, that's it. So thanks everybody.